Okay, Bismillahirrahmanirrahim. This is a video about the Gaussian Quadrature, one of the integration method in finite element method. This is on the course of the advanced numerical analysis. I am Asif Istiak. This course is supervised by Professor C. Joachim, and yep. From this video, we can learn what is Gauss quadrature rule, how we can calculate the integration, the problems of the integration, and how we can detect the point of the finite limit analysis applying these rules. Well, first of all, what is Gauss quadrature? Legendary Gauss quadrature rule is a quadratural numerical integration method, also called the Gaussian quadrature, or often legendary quadrature. A Gaussian quadrature over the interval of -1 to +1 with a weighting function of w of x is equal to 1. The quadrature order is 1 that are given by the roots of the legendary polynomials, that is Pn of x, which occur symmetrically about 0. Okay, so this is quite so difficult. However, we will detect the points. How we can detect the points applying this numerical integration method. So in the introduction, we will be introduced by the some of the basics of the Gauss quadrature rules or formulas. Actually, in numerical analysis, the quadrature rule is an approximation of the definition integral of a function, usually stated as a weighted sum of function which values at specific what can I say, specific points within the domain of the integration. And also, the polynomials of degree would be 2 twice n -1 or less by the suitable choice of the nodes. Well, the weights will be dependent on the n that will be discussed later. The weights w will be 1, 2, 3, 4. Sorry, not like that. From 1 to n, and I have told that before the range is -1 to 1. Well, this is the typically the formula of Gauss quadrature rule. This is for the single integration. So we will be introduce briefly the basic concept. We will solve the problems and how we can apply this integration method in FEM in 2D. So this you can see here the single integral, which is the integration of f of x. The interval is from the -1 to 1, and we will add the discrete functions one by one depending on the number of the n. Also, for double integral, we will integrate it for twice, and the limits will be obviously -1 to 1, and the equation will be like that. And this is for n is equal to 2. I will discuss it later. So for Gauss-Jacobi quadrature, which will not be discussed here, but I have put it here because the Gauss legendary quadrature rule is not typically used for integratable functions with n-point singularities. Instead of the integrand that can be written as like this. Okay, where you can see here the g of x is well approximated by a low degree of polynomials. Then alternative nodes, the alternative nodes which can be said x bar without x, it would be x prime I, and the weights would be x prime y. Sorry, the weights would be w prime I. That will usually give more accurate quadrature rules. These are known as Gauss-Jacobi quadrature, and this is like this. So we will not discuss this right now. And however, here I'm talking about the weights. Here the equation of the weights. We may discuss it later, but we will discuss it, the basic concepts with briefly, and we will try to know how we can apply it. So this is the some low order quadrature rules are obtained below the limit -1 to 1. Here, if the n is equal to 1, then we will put x, that will be 0, and the weights would be 2. If the n is equal to 2, then the x will have two values, that will be +1 by √3 and -1 by √3, and in that case the w will be 1 and 3. For 3, there will be the x's value will be 3, and the w's value would be 3 also. This is the w1, w2, and w3. This is quite boring, but let's get into the main topic. So for Gauss quadrature single integral, this is the formula, and if you wanna get the integral area here, then we need a function to define, which must be -1 to 1. And what can we do for this integration? Okay, so the result of this yx will be is the first order polynomial. If we follow the rules of the Gauss quadrature here, plugging the weight and the x depending on the n, then we will get the exact answer like the normal integration. However, we will know how to integrate it. So here you can see here the n, the node number is 1, the n is equal to 1. Where the n is equal to 1, where the x is equal to 0. So here I have defined n is equal to 1, that means the point is 1 where x is equal to 0. So let's relate the point is 1 and x is equal to 0 here. So what would be the weight of the integration? The weight of the integration will be 2. So let's plug in the w, the value of the w here to 2, and we will plug in the x value in the function right here. So we will do the math after that. So this is the basic. I have to do the math. So now here for the if we want to integrate the area for 2 point, actually this would be 2 point. So if we want to integrate the area in the 2 points, then you can see here the points are here 1 and 2. So for the 2 point, we will find the table. Where is 2? Here the n is equal to 2. Then the x value will be here according to the table. The x will be 2. I mean the value would be 2, and the value is +1 by √3 and -1 by √3. In that case, we will put minus value the x1 and plus value later. And what about the w? The w is 1 and there will be 2w, right? According to the, we will follow the number of values of the x is equal to number of the value of the w. So here the x value is, the number of x value are 2, so the number of w's value will be 2. However, previously the equation was like that. So since n is equal to 1, so their terms was just 1, but in that case, since n is equal to 2, the term will be 2, w1 f of x1, w2 f of x2, and this is basically third order polynomials. Why this is third order polynomials? Let's figure it out. We have discussed it because the order would be 2n minus 1, right? So if the n is equal to 2, if the n is equal to 2 here, then we can get from here 4 minus 1, 3. So from that, this is third order polynomial. Okay, so I have erased it. Now let's go for 3 points. If we define 3 points, then we will drag over the table. What is the 3? The n is equal to 3, so we will get the number of value of x is 3, so x1 will be minus root over 3 by 5, that is like that. X is equal to 0, then the plus value is 1. And how about the w? So the w would be, w1 would be like this one, w2 will be this one, and w3 will be this one. The w will just follow the ascending or descending rules of the x, which is following the okay. So so in the for the 3 points, we can get here w1 f of x1, w2 f of x2, and w3 f of x3. It's quite it seems like difficult, so let's solve an example here. So for that, this is an example, and so for calculating the integration with for calculating the example, we will follow some rules that we have so in the previous slides. I'm sorry, there will be some edit here. This will be single integral. Okay, so what about the order? The order will be this highest order 4, though, so 4 is equal to 2n minus 1. That means n is equal to 2.5, so we will take 3. So where is the 3 in the table? Here, the 3. So we will define x1, x2, and x3. So the x1 will be, so the x1 will be minus root over 3 by 5. Oh, there were some errors. Okay, the x1 will be minus root over 3 by 5, then x2 will be 0, then x3 will be plus root over 3 by 5. What about the w? So w will be 5 by 9, w1, w2 would be 8 by 9, and then w3 would be 5 by 9. Okay, so this is basically the function. If we define it right there, and we will divide into the formulas. Well, if we write f of x1, then we will plug in the x1 here. For f of x2, and for the f of x3. Then we have got the f of x1, f of x2 and f of x3. We will plug this f of x1, x2 and x3 into the main formula. So the main formula was like before: w1 f of x1, w2 f of x2, w3 f of x3. There are three terms because the n is equal to 3. If the n is equal to 4, then we will go down to the table and get the x and w value and plug in here f of x1, f of x2, f of x3 and f of x4, something like that, and the terms would be 4. However, if we plug in the value of f of x1, x2 and x3 and plug in also the w1, w2, w3, we can get the integral value like that. So this is how we can calculate the single Gauss quadrature single integral in the area. How about the double integral case? The double integral case, this is the basic formula, and this is the example. So what we will follow the same procedure like the single integral. So what about the order? So the higher order would be 2. So in that case 2 is equal to 2n minus 1. In that case n is equal to 1.5. So for this we will take 2 and we will take the value of x and w from the table where the n is equal to 2. Yeah. So I have made this error again, sorry. Okay, so x1 is equal to right now minus 1 by root 3, right, and x2 is equal to plus 1 by root 3, and in that case we need also the value of y. So without any hesitation, the y would be the same value of the x1 is equal to y1 and x2 is equal to y2. So we have got the x value and y value and w1, w2. So we'll plug in like the way of the Gauss quadrature double integral. So this is the equation. Instead of f of x1, we will input now f of x1 and y1. So the ultimate formula would be 2x1 square, 3x1, x2, x1 and y1, and 4y1 square. So we will plug in just this value and I have got this one, and I will follow. There are a point 2, so the variables are 2, so in that case these terms will be 4. Okay, and now if we express the total equation here, then it would be w1 square f of x1 y1, w1 w2 f of x1 y2, and w2 w1 this one, w2 square this one. So in that case we will plug in all the values of the functions and all the values of w1 and w2, and by applying this we can get the integral value, exact integral value following the Gauss quadrature double integral. So this is how we can get the area by following the Gauss quadrature integration method. So now we will see how this is applicable in FEA. I have demonstrated this one in 2 dimensions. So first of all, this is the one integration point. For the quadrature approach is applied both integrals while evaluating both integrals. So now we can see here, if we follow the double integral rule, for the 1 point this should be mainly 2 points. However, if we want to follow the single point, then the point will be 1, right? So where is the point? This, say for example, this is the point, so it is called the reduced integration. The reduced integration is a integration for a linear Q4 element for 1 point here. So we will just plug in the value of x1 and y1 right here, and what is the w's value? The w's value is 2, so 2 into 2, f of 0 and 0. So forget about this one. This is actually the equation is like that. So this is the reduced integration for one integration point in 2D. So this is how we can detect one point by Gaussian quadrature in finite element analysis. How about 2:2 integration point? So in this case, full integration of a linear element that is Q4 will provide us the exact good result, and the reduced integration Q8 is quite incomplete result. So we will get, if we follow the this formula, then we can see here 1.234. So for n is equal to 2, we have two variables, so in that case the points are 4. Yeah, from that equation, from the formula, we can get the 4 points. We can integrate the total area of the 4 points that we have demonstrated before, and we will now demonstrate the exact points of these 4 locations. So how can we do that? This is how we have done the integration for the area for 4 points, 3 1 1 3. The points were x1 y1, x1 y2, x2 y1, and x2 y2. And with these 4 points, there is an area, and we have solved the equations to get the area value. However, now we will get these points. How we can get that? So let's do it. Now the equation was like that. So the equation was like that, and what is the value of x1 y1, x2 y2? This is the value which we have gotten from this table, and yeah, we will input these values into this equation, and we will figure out where the 4 points are. Okay, so here you can see here f of -1 root over 3 minus 1 by root over 3, which is the 4th coordinate. So here is the first point. What about the second point? This is 1 plus and minus, so we will go to plus up to 1 by root 3 and go lower for the value of 1 by root 3. So yeah, and what about this one? This is 3, because here you can see there plus and plus, so I will go plus to the x-axis, plus to the y-axis. And this is for the 4th points location. You can go you have to go to locate these points, minus 1 by root 3, minus 1 by root 3, and plus 1 by root 3. Oh, this would be just slightly here. However, this is how we can get the 2 by 2 integration point following the Gauss quadrature rules. Okay, so and we can also integrate, we can also calculate the area captured by these points by following this procedure. Okay, now we will go through another one, that would be, yeah, we'll go 3 by 3 integration point. Okay, so before going to this slide, we'll recap the previous slides. So in the double integral, we had followed this one, x1 y1, x2 y2, and x2 y1. For the 4 points we have gotten the result, right? However, how about if the higher order is 3 instead of 2? So if the higher order is 3, then the n would be 3. So in that case, we will get n is equal to 3. So for that case, the number of x value will be 3. So if the number of the x value is 3, then we can get 3 y value. So for after combination, we can get 3 into 3, 9 points, right? In the previous case, we got x1 and x2. Sorry, x1, y1, x2, y2. So from this one, 2 is to 2, sorry, 2 into 2, we have got 4 points. So now in this case, we have 3 values of x and 3 values of y. So we will get 3 into 3, 9 points. So in the same way, we'll just put the formula here. In the formula there were 4 terms, but now since we have 9 points, then we have 9 terms, 1 2 3 4 5 6 7 8 9. How about the value? So we'll input the value w1 square, that is 5 by 9 whole square, and we will get the x1 square, then this is x1, and after that we will get x1 y2, this is x1 y2, like that, and this is we will just follow the formula here, and we will input the value of x1 y1, or it is x2 or x3 or whatever, and we will input also the value of w here, and we can get the total form like this. And from this equation, we can detect where the point is located. So if we go through this one, then the coordinate is minus root over 3 by 5. We'll go to the minus of the x-axis, and also and go downwards, minus and minus, then we will go left and go down. And for this is minus x and 0, so we will get this point. And what about this one? Minus value of x and plus value of y. So minus of x plus of y, 3. What about the fourth point? 0 and minus 3, 0 and minus 3. What about this one? 0 0, so it would be like here. Yes. And what would be this? This is 0 plus, so 0 plus this point. What about this one? Plus minus, so we will go plus to the x-axis, minus to the y-axis, and yeah, here is the point, and the value would be like that, obviously. And what about this one? This one is here and this one is here. So yeah, from this 3 by 3 integration point we can get the 3 points location, and we can also calculate the whole area by following the Gauss quadrature rules. So from this video, what we can understand that the Gauss quadrature is basic knowledge, the single and double integration rule, how we can get the we can integrate the area, and how we can locate the points. Thank you. This is the reference I have followed. Thank you.